All right, welcome back to Tolleson Physics. So what we're going to look at today is how does an external force change the momentum of an object? And so we're actually going to use a force versus time graph to help do something like that. So in a separate video, we took some data where we looked at area under the curve of a force versus time graph. And that actually gives us the impulse. And so we're going to look at an example just like that. And so let's consider a simple case, right? Let's consider that I have a box, and this particular box is, let's say, 10 kilograms. We're going to be on a frictionless surface, and we're going to apply a force to this. All right? So the force is going to be measured using a force gauge. We're going to have time in seconds. We're going to have force in newtons. And so I'm going to make this a fairly simple looking force gauge. Well, no, let's actually change the force. Let's make it interesting. So what I'm going to do is I'm going to, let's say, have a force. I'm going to increase the force, and then I'm going to decrease the force. So things are changing. That's okay. We can actually handle that. And so how is it changing? Let's say that I'm only pushing it for 10 seconds, and let's say this peak happens at 5 seconds, and let's say that that peak is 20 newtons. All right? So that is the force. So now I have a changing force. We really haven't dealt with a changing force before, but this force versus time graph allows us to do it. So let's think about how would conservation of momentum help us? We're going to start with an initial velocity of 0. All right, so conservation of momentum. I have the sum of all my initial momentum plus the impulse equals the final momentum. All right, so how do I piece this all together? Well, in this particular case, this is a force versus time graph. That's a multiplication. That's a multiplication. So this graph tells me this number. So let's look at it. So what did I do? I got 20 times 5, but it's a triangle divided by 2, but it's two triangles of the same size. So this really does end up being 20 times 5. So I have an impulse. So the impulse is going to equal 100 Newton seconds. That's what that number is. What's the starting number? Well, mass times velocity equals 0. So I have 0 plus this 100 Newton seconds, and that's going to equal the mass of my block, which I said was 10 kilograms, times its velocity. Well, I can solve for that, right? So if I divide both sides, I get velocity equals 100 Newton seconds divided by 10 kilograms. And so that equals 10. Now, does Newton seconds divided by kilograms make sense? Well, let's just do a quick unit analysis. Newton is kilograms, meters per second squared. And then I have to add the other units. So I have a second and I have a kilogram. Does that equal meters per second? Kilogram, kilogram cancels. One of the seconds cancel, and lo and behold, I end up with meters per second. All right, so I can use this idea of a force versus time graph, simple shapes, simple geometry. I can figure out the area under the curve, and that tells me the impulse. And then knowing that impulse, it actually can tell me how the momentum of the system changes. And so this is how you can use graphical methods to be able to figure out a change in momentum. All right, so the best way to learn physics is to do physics. So here is the problem from the video. Hit pause, give this another try, and then see what the solution is. All right, here's the solution that we went over in the video. If you have any questions, you can go back and look at how it was solved in the video.
Here's a new problem. So now try this new problem where the block is now moving at 4 meters per second. We have a different force versus time graph, so you use that to figure out the impulse and ultimately what the final velocity of the block is. Hit pause now to solve the problem. All right, here's the solution to the problem where the area under the curve ended up being 70 Newton seconds. And when you look at conservation of momentum, the solution ends up being 18 meters per second to the right. So keep practicing so you can get better, and we'll see you next time.